Thank you, Uganda, for that introduction. My name is Maurice Johnson. I'll be one of the co-presenters today. Um, our topic is going to be over 6920, proactive traffic signal timing and coordination for congestion mitigation on the arterial roads. We would like to thank Dr. Xing Wu and Hao Yang with Lamar University for their help on this research and working in collaboration with the Houston District for TxDOT. Over the next 100 slides, joking, 30 or so slides, we'll be giving some background information on our research topic, what the objectives were, what proactive signal control and concept is, some simulation results, our field experiment, summary, and how we look to put this on a large scale. Traffic congestion is not something that affects large cities and small cities. It affects all of us on our daily commutes. As you can see nationally, 5 million hours of delay are added on those commutes. The financial cost is $100 billion. In the Houston area alone, 60 hours of delay are added annually for each commuter, and those numbers are expected to increase to 100 hours in 2025, which translates to $12 billion in financial loss. To put that in perspective, the Houston commuters could have bought the Houston Astros 5 or 6 times. For the Houston district, TxDOT operates and maintains over 1,000 signals. At those locations, we operate them either on fixed time, which means the phase sequence and duration of each phase is already predefined, or actuated control, or sometimes we call free operation, where the phase sequence and the interval is dependent upon the detection and the vehicle demand at that intersection. Where we would like to get to is what I would call proactive control. And this is when the phase at each time interval is assigned to the one with the highest predicted delay based on the short-term predicted timing and traffic volume. Our research objectives was to develop a fully collaborative vehicle signals control system and also optimize the performance of the signalized intersection. Here we see a illustration showing the vehicles at the intersection and the communication that is taking place between the vehicles and signals and the detection. There's probably a few vehicles that are probably texting with one another or people at home, but we're not going to use them in this particular illustration. What our goal is to optimize the phase assignment and duration without being restricted by the cycle length, and also optimize the signal and phasing of the multiple signal plans. Okay, to determine which phase will get the green, what we'll need to do first is calculate the delay at each approach. This equation below shows you how to calculate that delay. Once the delay is calculated at all the approaches of the intersection, now we'll look to select the approach with the highest delay. And utilizing this signal optimization algorithm, we can now look to optimize the signal at this particular intersection. To see how this will work, we'll start at time interval T. Once the current delay calculations are found, we can start receiving and getting information with the connected vehicles as far as whether the vehicle is at within the intersection, the distance it is, and also the miles per hour of that location. Here, we will start calculating the predicted delay at phase 1 of the intersection, going all the way to phase P of the intersection. And based on the approach with the highest delay, that's the one we will look to select first. And now we can start looking at optimal phasing at this particular intersection. To test our simulation on this, We use FM 1960, which is in Northwest Houston. The 4 intersection that was chosen was Worthing Boulevard, North Eldridge Parkway, Windermere Lake, and Fallbrook. The total length of those 4 locations came out to be 7,713 feet, with the posted speed limit of 40 miles per hour. Unless you've driven on it, it could be a little higher. The number of lanes on 1960 is 3 lanes, each direction for the through movements, and 1 left turn lane in both directions. For the minor road or cross streets, the speed limit varies from 30 miles per hour on Windermere to up to 40 miles per hour on North Eldridge Parkway. All right, just to recap on what we're looking to do. First, we will need to collect the data at the location, needing to know what the geometric properties are. We will also have to have the existing signal plans. Data collection will be needed with the volume and occupancy. Now we can start building and modeling our intersection with our integration software, which was provided by our research group, and also they will be also using VISM. Comparison was made based on the simulated and observed traffic flow for verification, and now we'll be looking to implement our proactive signal control in our simulation. Once that is done, we can now look to take this out into the field to test. Our data collection was performed on April 1st, 2016 through April 7th of 2016. We started our collection at 11 a.m. and continued all the way through 7 p.m. The data was collected from the loop detectors every minute, and we summarized this in a 15-minute intervals. Here we see the hourly volume for phase 5, which is the left turn movement on the Eldridge Parkway. As you can see, top of the graph, it shows that the vehicles per hour was at 120 vehicles per hour, which is during our PM peak periods, and as low as 20 in our off-peak periods, which was after midnight. We also looking at the same location for our occupancy on phase 5, which was the left turn movement, and it compares same with the vehicle per hours. Our occupancy shows at 90% during our PM peak periods and drops down below 10 in our off-peak periods. And that concludes my portion, and now I will turn it over to Steve Chiu.
Good afternoon. So once we gather all these data, what do we do with this data is kind of critical. So what we did is we run the data through a simulation, basically integration and the VISM simulation, and we try to predict, see if our simulation can match our field data. Because that'll become critical, because if your simulation is 100% correct to your field data, basically you can predict the traffic up to that point, because you know exactly what time when your volume picks up and when it drops. So this is one of the direction we're testing on. This is the field data we collected for the eastbound weekday traffic. And as you can see, the data is between the simulation and the field data is, to me, it seems very close for this one. But this one, for the westbound outflow, is a little bit off a little bit, because you can tell the data right here is a little bit not found exactly to the field data is. But we do what we can. So once you have the equation or the simulation for the modeling, you crank that into an algorithm, basically the proactive algorithm, and you'll calculate how much benefit you'll get based on the algorithm it's predicting. And this is what the system show you that, okay, this is how much I would be saving as to the time delay and stop delay and all the benefit you get from the proactive system. And this is a max and Q delay. Assume we can reduce the queuing and also the average delay on each direction. And during the weekday and weekends. Okay, so what we're going to do is we're going to put it in the one test location. And the location we pick for the actual testing, because all that previous one, 1960, just it's a theoretical value. It's not the actual value we implement on the field. So we got to test in the field, actual field location. So the field location we pick is a NASA row one of the location, small location, because we don't want to have too much impact to the traffic in case this thing didn't go well as we planned. So we pick a location a little bit more remote to test. And this location has the 5 approaches or 5 phases. And we all have stop bar detection and then a couple of advanced detection or setback detection. And what we want to look for is how we evaluate the system. We try to look for the benefit of volume. Do we increase the volume flow or also complain? That's how the 2 measurements we try to accomplish. So what we're looking for, since there's a limitation what we can do with the controller is not at the advanced at the point as where we wish it can be. So basically we just pick 2 variables we think we can use. One's the volume, one's occupancy. And the value is selected by, I provide them data for about a whole week worth of data, and they crunch it through the algorithm and created some sort of volume and occupancy. That's critical to the intersection, where I need to watch out for. So basically, we just program that into our controller. So we'll create some sort of logic statement in our controller to obey this rule, but we apply to all approaches. So we don't know which approach has more volume or occupancy than the other approach. So each approach can override each other based on its demand and occupancy. And all the numbers shown in red, the volume and occupancy, it's all created by all calculated through the algorithm software. And we changed a couple of parameters. Part of it is the min time, the max time, and also the vehicle extension time. These are very basic parameters we change in the controller. And this is one of these are the researcher. The taller guy, he's Dr. Hao. He's one of the primary investigator, a principal investigator for the research, and the other one is his grad student. So what we did at the site is that before we turn on for actual data collection, we let them fine tune the volume and occupancy for about 2 weeks or period before we actually say we go out there collecting data. So the actual day collecting data is those are 2 days. November 22nd, we have a system turned on, and then December 9th, we turn the system off. So we can do a comparison between the two data. So based on our experiment, based on our data collected or observation, it calculated that we have quite a lot of benefit out of this system. We reduce reduce delay by 11%, and stop delay about 29%, and total delay about 13%. And we also increase average speed a little bit. So how does that translate? But that just gave you some general idea. So this is what we see on the field. This is a left turn on weekdays. And we can see a little bit benefit between the red is an after, and the blue is before. So you see a little bit benefit out of the left turn because it's very, very low volume. But we should see some benefit out of this system. And this is a weekend. Same thing in left turn. And it's not drastic. You don't see the big benefit out of the system, but you still see a little bit improvement on the system. And this is the through movement for the phase 6, we only can see a little benefit out of this little peak during the weekdays. And this is weekend for the same direction, but we see a lot more benefit out of during the weekends. So overall, for this location, our average Q length actually decreased by 60%, and the maximum Q length decreased by 46%, and some minor approach, you also see some benefit out of it. And overall, if we can put in what we can, if we can operate this as a 100% proactive signal, we actually can get a lot of benefit out of this system. And we can reduce the delay, and also the air quality can be improved. And even the field test shows a lot of good improvement. And since we deployed this location, we haven't heard any complaint from anybody. So to me, that's a good feedback, because typically you get a lot of complaint from people if you got a system it's not doing correctly. And we also save a lot of reduction in the waiting time, the delay time. And this one is very just one general one location, so this does not represent the whole system. So what we're going to do right now is on the phase 2 of the implementation is that we're going to do 30 more intersections. So this corridor, this 30 intersection, a little bit more different, not a little bit more different now. We're going to test more different criteria now. Basically, we're going to test different traffic volume, different type of detection system, and different driver behavior, and coordinated or free, and some of these locations are diamond intersections. From our preliminary data from FM528, we already deployed the FM528 system already. And that location has 3 intersections. And the spacing for that intersection is kind of a little bit unique, because it's coordinated during the AM peak and PM peak, but it's operating free during the non-peak hour. And so we want to see, okay, how does this system let us give us what kind of feedback we're getting it. So based on our earlier data collection, we found out that free operations sometimes work better than coordinated, period. Because when you run it fully coordinated, you will not allow system do what it needs to be accomplished. So what we're going to do right now is we're going to modify our algorithm a little bit. So we're going to try to figure out how we can drop the intersection back to free operation when it's need to, and went back to coordination when it's need to. So right now, research, we're still crunching all these data in there, and hopefully we can automate that to a certain extent. And our goal, what we try to accomplish is that if we can for some way to program that entire algorithm into a controller, and because you always have something cause and effect. Every time you change your volume or occupancy in the logic statement, it'll affect your outcome for next cycle. So for right now, we have to do that manually out in the field. We have to observe it, and then, okay, that's fine, tune it, change the volume occupancy to a certain value, and observe again, and tune that again. So if you can some way to automate that, let the control itself to learn all the process itself. So basically, it'll adjust itself based on what's field condition. So that's how we try to figure if we can somehow automate that. So we want the machine to be able to self-learn. So when we do that, then we prefer machine learning. So basically, it'll learn itself. It'll adjust based on volume and occupancy itself. So basically, we can just have a hands-off after that point. Any questions? Yes.
Just one quick comment. I guess in your study, you mentioned you're using the predicted delay as a criteria to assign the green time, and under you also
Okay, I guess I just have a quick comment. I mean, I guess, man, I forgot what I said. Anyway, I mean, you developed an algorithm using predictive delay to assign green time in a connected vehicle environment. Basically, the controller knows all the vehicles in the intersection,
Yes.
so it can easily achieve your algorithm. But for example, if we have like a perfect detection, like a stop bar plus all the detection in the approach, I mean, it will achieve the same, I would say same results. I mean, and like a connected vehicle not only give the the capability
Yes,
that
yes.
sensing all the vehicles in the department in the intersection, but it also allows us to do many other things like eco-driving type of situation and other things. So I'm very glad to see you look at a connected vehicle impact in this study. Really good.
Yes, and also I didn't mention that on our part of second part of phase 2 study, we had one of those 30 intersections. We test also different type of detection layouts. One of our corridor is a design for adaptive system. So basically, we have a lane-by-lane detection system, and every detection designed to run in adaptive system. So I'm very curious of how this system operate in that type of environment. Hopefully, it can give us more positive feedback compared to typical 6x20 loops or 6x40 loops, or a system is not designed for those high adaptive data collection system. So that's something we try to hope we can get information from. And of course, the benefit will be best if we have all connected vehicle. But that's the direction we're pushing through right now. But in the meantime, we should have to figure out what's in transition stage, how we take care of the in-between stage. That's required high accuracy of detection system. That's why we are testing on that aspect also to get enough information to implement the system.